In the previous batch of videos, we looked at difference equations, which were equations of the form an plus 1 equals an plus delta A, where the idea was we were trying to describe some system that was changing over time. And so we represented this by recognizing that any changes can be represented as the new value is equal to the old value plus the change. And so we looked at a variety of different ways of trying to describe change and then also describe how this sort of equation changes over time. The one thing that we limited ourselves to in all those previous examples is we looked exclusively at systems where a single variable described what was going on. And that's actually a quite limiting set of problems. More often than not, when you're trying to describe a dynamical system, there are actually multiple variables that are changing, and we'd like to account for the changes in all of them all at once. And so today we're going to look at systems of difference equations. They're going to look very similar. We're still going to have the same sort of general framework. It's going to be new value equals old value plus the change. But the difference is that xn, the state, is now going to be something like it's going to be a vector which has components. Maybe it has n components. And the change is now not going to be just a regular scalar valued function, but rather f is going to be a function that takes in an n-dimensional vector and spits out an n-dimensional vector. Okay, so you put in this current state of the system. You could also potentially have time dependence there as well, although we won't look at many examples of that. But the output then needs to be the change in each of those individual variables. All right, so let's look at an example of this. We're going to start with a very simple example, and we're going to come back to this a number of times because it's good for illustrating some of the techniques needed to describe difference equations. So the scenario is that we have a rental car company, and they distribute vehicles out of Orlando and Tampa. And each day, some of the cars that are in Orlando end up getting returned in Tampa, and some of the cars that are in Tampa end up getting returned in Orlando. And what we'd like to know is what's going to happen to the number of vehicles at each place over time. And you can imagine this being important because if the number of vehicles stay relatively constant, then maybe we don't really need to worry about having or paying someone to actually transport vehicles from one location to the other. We can just let our customers take care of that for us. But on the other hand, if all of the vehicles are going to end up in one of the two locations, then obviously that's a problem. And so we're going to have to adjust our business model to pay for people to balance out the number of cars in each place. All right, so how do we describe this? Well, first off, let's think about the state of the system. In order to know what's going on, we need to know two things. We need to know the number of cars in Orlando, and we need to know the number of cars in Tampa. And so we could represent the state variable, which I'm going to call xn, with a two-component vector, the first component being number of cars in Orlando after n days, and the second component being the number of cars in Tampa after n days. All right, so we now want to write down a difference equation to describe this. And notice that we can say is that the new values of the two variables can be written out in terms of the old values because we know exactly where every car that ends up in Orlando came from. So if you think about just Orlando for a second, on any given day, 60% of the cars that are in Orlando are going to stay in Orlando. So the new value of ON will include 60, and that's ON, not 0N, 0.6, so 60% times ON. And then the other cars that are in Orlando on day N plus 1 must have come from Tampa, and that's going to be 30% of the cars that were in Tampa on the previous day. The same sort of reasoning can be applied to Tampa. Where did the cars who were in Tampa on day N plus 1 come from? Well, 70% of them, or 70% of the cars that were in Tampa the day before stayed there. So 0.7 TN stayed, and they will be included in TN plus 1. And then the rest of the cars came from Orlando, and we know that 40% of the ones in Orlando the previous day will actually arrive in Tampa. And so our difference equation can be written right there. So there I've actually included, this is actually xn plus f of xn all rolled into one expression. Okay, sometimes it's more convenient to think of it that way, sometimes it's not. In this particular case, because we weren't really keeping track of the change directly, we were thinking about where the cars came from. We can use this framework where we deal with both xn and f of xn all at once. All right, so there's our model. And here I've written it out as two equations, but you could easily, just as easily think about that as a vector valued equation. But what I want you to note here is that what we have is a linear equation because each of the variables is multiplied by a constant. And there's just a linear combination of our variables on the right-hand side of each equation. So this is a linear equation. And more generally, linear equations can be written as the form xn plus 1 equals some matrix A times xn plus some constant vector B. In this case, we actually don't have a vector B, but we can find a matrix A if we take those coefficients and put them in a matrix. 0.6, 0.3, 0.4, 0.7. If we multiply that matrix by ON TN, we get precisely the right-hand side of the equation here. And so that gives us the state at time n plus 1. Okay? And so we could think of that as being plus 0, 0. Which means this is indeed a linear difference equation. All right. So that is how we set up the model. And then we can start to ask questions like what happens to ON and TN in the long run? Can we actually plot out how they're changing over time? And to do that, it would be very helpful to have a computer because as we saw with even a single variable, updating the state for future times can be very tedious. With multiple state variables, it gets even more annoying. And so we're mostly going to rely on MATLAB or Octave to help us with that. All right, so we've got our model. How can we simulate this with the help of a computer? Well, to start off, we need two pieces of information. We need the update formula, and we need the initial state. You can't figure out how many cars there are going to be in the future if we don't actually know the state at the present time. So we'll need to specify our initial condition. In this case, I'm going to assume that we have 5,000 cars in Orlando and 2,000 in Tampa. And we can include that in our code by creating a column vector. So that's the second line here. This is creating a vector or a matrix X. It says the colon means all rows, and the 1 means first column. So the first column with all rows is going to be 5,000, semicolon, 2,000. Recall that semicolons end a line or end a row in a matrix. And so this is going to be a 2-by-1 matrix currently. All right, so we've included X. And then we've also specified our matrix A. And again, commas or spaces can be used to separate entries, and semicolons and lines. And so this is the matrix 0.6, 0.3, 0.4, 0.7 with its 2-by-2. All right, once you've specified all of those pieces of information needed to set up the model, we can start updating the solution. And so what we'll do is we'll use a for loop. Recall that when you say for k equals 1 to colon n, that's going to repeat the same command with k equals 1, 2, 3, 4, all the way on up to n, and including n. Okay, so the first time we go through this loop, what it's going to say is take the matrix A and multiply by the first column, because k is 1. The first column of x, and actually x only has one column at this point. And what it's going to do is create the second column. So it's going to store the new values for Orlando and Tampa in the second column. Okay, so that finishes the first loop. You hit the end command, and then you go back up to the top. Now k is 2, and so instead of updating the first column, you're now going to take the second column and multiply by a, and now you'll get the third. And that's going to repeat until we've created columns 1 through n plus 1, meaning we've got the initial state plus the n next states. And so X will end up looking something like this. It'll be 5,000, 2,000 in the first column, and then all subsequent columns will be the updated states from there. Okay? Once you've got that solution, you can start to generate plots. And so here I've actually plotted this solution out in the slides, but I think it's actually helpful to see the entire code needed to generate the plots as well. And so let me shift gears for just a moment. Bring up Octave. All right, and so here's a script that I wrote to simulate this process and to generate some plots. And I'll just walk you through it so you can maybe adapt this sort of thing for some of your homework problems when you're studying systems of difference equations. So first thing, these first 3 lines are for just giving me a blank slate. Those clear out all the old variables, it closes any open figure windows, and it deletes the old command history in the command window. So I'm starting from fresh. I've introduced 2 parameters, fs and ms, which I'm going to use for the font size and the marker size in my plots. I like that because I want my plots to look pretty and I want to be able to adjust things relatively easily. Okay, next we're going to set up the problem. We're going to first specify the number of steps that we want to take. And then we're going to specify our matrix A and then our initial state. And so I will switch this to 5,000, 2,000. And then this last line here, this is to specify exactly where and how big your figure window is, where it appears on your screen. And I'm doing that for the purposes of the video. I want you actually to be able to see it. So don't worry so much about that. All right, so after specifying my initial state, I will add that as the first column in my matrix X. I'll have that for loop that we talked about a moment ago, and that should generate the solution. And once you've got that, we want to plot the results. And so the plot command generates a graph. You give it the X variable, and so here I'm giving it the X variables 0, 1, 2, 3 on up to N. So those are the times where we're going to be plotting the solution. And then I want to plot, well, I'm going to plot the first row. So X parentheses 1, the first index means the row number. And so I'm going to give it row 1, and I put a colon because I want all of the columns. And so this is again going to extract the entire first row from that matrix, which corresponds to Orlando. If you want to get a little bit fancy, you can start to specify colors and marker sizes. So I'm going to use circles and the color blue. That's what the O and the B represent. And I'm going to make the markers size 20 so they're a little easier to read. And then hold on tells MATLAB or Octave to don't overwrite the plot, but continue plotting on top of what you have before. And so on the next line, I will plot, again, the same range of times, 0, 1, 2, 3, up to N. And then I want to show the second column, so the car is in Tampa. And I'm going to use little plus signs that are red to mark in each individual data point. And then you can also add labels. So here I'm going to label N for the step and cars for the y-axis. And then you can specify the font size as well. And if you want to even change the font on your axes, you can use this set command. And lastly, I'm going to include a legend to label the 2 curves, so it'll indicate that the blue is Orlando and the red is Tampa. All right, all the stuff that's in green you could ignore. That's commented out right now, and so we don't need to worry about that at the moment. But let's go ahead and run this. And there you go. It looks like what we've got is at time 0, Orlando has 5,000 and Tampa has 2,000. After 1 day, Orlando has maybe 3,600 or so, and Tampa has around 3,400. And then Orlando is going to have maybe 3,200 versus 3,800. And it looks like both values are leveling off and approaching some value. Okay, so in a couple of days, we will look at how you actually compute exactly what the system is going to approach in the long run. For now, we could just estimate it numerically, and from what I'm seeing, it looks awfully close to 4,000 and 3,000 for the final values. And so at that point, now that we've solved this numerically, we can ask ourselves the question, is that acceptable? You know, if you're running this rental car business, is it okay to have 4,000 cars in Tampa and 3,000 cars in Orlando at the end of each or after a few days? If not, then you may need to schedule someone to move cars from one location to the other. And if it is okay, then you can be pretty confident that, well, you don't, you know, if 4,000, 3,000 is okay, you don't need to actually schedule that. All right, so that's a numerical solution. Now let's think about analytical solutions. So let me go back to my whiteboard here. So we had the model. Xn plus 1 is equal to A times Xn. And we had some initial value X0. And so let's, we won't fill in the actual numbers, but let's see if we can find the pattern here. So if I want to find X1, that corresponds to a value of n equals 0 in the equation above. And that would be given by A times X0. And if I want to find the next state, I would take A times X1. But since we already know X1, notice that that can be written as A squared times X0, right? We're going to have A times X0, which is the same thing as A squared. And X3 is going to be A times X2, which means we're going to get one more factor of A. And so given that pattern, it looks like the state of the system at time n is going to be A raised to the n times X0. All right, so there's our analytical solution. We know exactly how to compute how many cars are going to be in each state at each point in time. We just need to multiply the initial state by the matrix A n times. Now, this is where you may recognize that some linear algebra would be particularly useful, because computing A raised to the nth power when n is large is, well, it could be very computationally intensive. But the good news is, in linear algebra, you learn about techniques like finding eigenvalues and eigenvectors, diagonalization, and other things like that, which can actually be used to simplify this sorts of calculations dramatically. So in a future video, we will actually review a little bit about those concepts and see how we can use those to help us simplify this equation even further. All right, we'll stop there. And in the next video, we'll talk about epidemic models.